Hello everyone, welcome back to the last video of the Regents review series. In this video, we're going to talk about nuclear chemistry. So nuclear chemistry, let's start with the very basic idea that nuclear chemistry revolves around, and that is the stability of the nucleus. So when we say that a nucleus is stable, we are kind of referring to the proton to neutron ratio in that nucleus. So in a stable nucleus, we want that ratio to be as close to 1 as possible. For example, here we have two isotopes of oxygen. One of them is oxygen 16, the other is oxygen 18. So oxygen 16 has 8 protons and 8 neutrons. So the proton to neutron ratio is 1:1, but in oxygen 18 we have 8 protons and 10 neutrons, so the ratio is very far from 1:1. Kind of a sweet spot to say that this ratio is somewhere closer to 1:1 is that if you have a ratio of 1 and 1:2, that is kind of like where you want to call it off. So if it's like 1:2 is like fine, we'll still consider that stable. But if it's like a ratio of 1:1.3, that is considered unstable. And then if we go a little below, then maybe somewhere around a ratio of 1:0.8 will be, or anything above that will be considered stable, but anything below 0.8 will be considered unstable. So that's like a sweet spot to make a decision. So what happens to these unstable nuclei then? They are called radioisotopes, because the reason why they are radioisotopes is because they still want to be stable, and to become stable they emit decay particles. And this phenomena of the radioisotopes emitting the decay particles, different type of radiations and stuff, to as they are trying to become stable, is called radioactivity. Okay, so in terms of decay particles, we are given a set of decay particles in table O. Please make sure that you familiarize yourselves with all of them. It's only 6 decay particles. The thing to keep in mind, however, is that if you look at these decay particles, and this is true across the board for nuclear chemistry, that whenever we are given this isotopic notation, the number at the top represents the mass and the number at the bottom represents the charge. So for the alpha particles, the mass is 4 and the charge is +2. For the beta particles, then the mass is 0 and the charge is -1. So that's how these numbers work. And so after emitting the decay particle, the radioisotope then converts into a different element, or a different radioisotope. So this phenomena where we have a radioisotope undergoing decay to convert into a different radioisotope is called a transmutation. Okay, so we can have different types of transmutations, natural or artificial, but just radioisotopes converting into different radioisotopes is called transmutation. So let's talk a little bit more about the decay particles. So referring back to table O, we are going to focus on alpha, beta, and gamma. So here what you can see is a comparison of the penetrating power of alpha, beta, and gamma particles. So and the neutron as well. So as you can see over here, neutron seems to go through most of the things, right? But in general, normally you're, for the Regents exam, you're only asked to compare alpha, beta, and gamma. So out of those three, you would say that gamma has the highest penetrating power, because as you can see, gamma is able to pass through most of the things. So it is the strongest out of the first three, and those three are the most common types of decays. And then another thing that you can get about the decay particles to compare them is, what if we let alpha, beta, and gamma radiation slash particles, what if we let them pass through an electric field? So as you can see in this picture, the beta particle is bending towards the positive side, and that's because remember that the charge of a beta particle is -1. right? And then we see that alpha particle is bending towards the negative side, and that's because the charge of an alpha particle is positive 2. So remember, in chemistry, opposite charges attract. So the thing that has the positive charge is going to bend towards the negative thing. The one that have the one that has the negative charge is going to bend towards the positive side. And then gamma, as you can see, does not bend towards any side because gamma has a neutral charge. So it has a charge of 0. And that's because gamma is just radiation. It's just energy. All right. So we talked about all of that. So let's move on to discussing the two different types of new transmutations that I mentioned, natural and artificial. So natural transmutations are just natural decay. So this is spontaneous, meaning we don't need any energy for these to occur. So there's normally only one reactant in case of natural transmutations, which is a radioisotope. You can see this example at the bottom. So we see one reactant only, and it's emitting a decay particle, alpha particle in this case, and converting into uranium. Okay, so convert, or maybe I should say decaying into a different radioisotope. So any type of natural decay is an example of a natural transmutation. So we are given the decay modes of some radioisotopes in table N. But these are pretty much all of the radioisotopes that you need for the Regents exam. So let's practice how can we use this table to work with some of the examples. So you're given the nuclei, their decay modes. So here's an example. It's asking uranium-238 is converting into thallium-234. What is it emitting? So if we want to figure out what is uranium-238 emitting, you can, of course, try to find uranium-238 in the table, which is right here, and you can see that the decay mode says it's an alpha decay. So that is one way to do this. Another way, which of course we want to practice, is to do the math. So remember that the mass and charge on both sides should be equal. That's kind of the biggest thing that you want to remember here. Mass and charge on both sides must be equal. So if we, on the reactant side, the mass is 238 and the charge is 92, we want the same mass and charge on the other side. But right now we only have 234 and 90. So we do 238 minus 234, that gives us a 4. And then we do 92 minus 90, that gives us a charge of 2. So you look at your decay particles table, table O, and you see which decay particle has a mass of 4 and charge of 2. And that turns out to be your alpha particle. Okay, so that's how you do this. And then let's look at another example. So here we have francium 220, and they did not give us either the decay particle or the element, the radioisotope that it's converting into. So we're gonna have to go ahead and find francium. So francium 220 is right here, and we see that this one is emitting an alpha particle. So we can go ahead and write an alpha particle here. And then we got to figure out what is it converting into. So 220 minus 4, that is about 216. And then 87 minus 2, that is an 85. So now we want to figure out which element is this that has an atomic number of 85. Remember, the identity of elements depends on the number of protons, not the mass number, because mass number can change if we have different isotopes of the same element. So we look at the periodic table, see which element has the atomic number of 85. That turns out to be astatine. So this is your answer. So remember, if you're looking for decay particles, you look at table O. If you're looking for elements, you look at the periodic table. So artificial transmutations then are non-spontaneous. These are the ones that require energy to occur. So we mostly have two reactants. In most cases, one of them is a radioisotope and the other could be like a decay particle or something. But sometimes both of them could be radioisotopes. So in this case over here, you see that we have an aluminum combining with a decay particle. So it's converting into phosphorus and emitting a neutron. So here is an example of an artificial transmutation. So let's do this work to figure out what is aluminum converting into. It's slightly different than the one that we saw previously, because this aluminum is combining with an electron. So 27 plus 0. First of all, let's go ahead and count the total mass and charge on this side. So 27 plus 0, that gives us 27, and then 13 plus minus 1, that gives us 12. So this is the mass and charge that we should have on the other side. So 27 minus 1, that gives us 26 as the mass of this substance. And then 12 minus 0, that gives us 12 as the charge of the substance. So you go to your table and periodic table, and you figure out which element has the atomic number of 12. So that turns out to be magnesium. So some common examples of our artificial transmutation are nuclear fission and nuclear fusion. For both of them, very, very important thing to remember, for both of them, mass is converted into charge. So even though when we do the math, the mass kind of turns out to be the same on both sides, but just remember that some of the mass of the reactants is converted into energy. So let's look at the very specific examples of fission and fusion that we know of and that we know occur. If you are given 4 options and you are asked to identify an example of a fission or a fusion, please only select the examples that we are going to talk about now. If you see other examples of like artificial transmutation, for example, something like this, remember that yes, this is an artificial transmutation, but this is not necessarily fission or fusion. So fission reaction is when there is splitting of a larger nuclei into smaller nuclei. And while that is happening, there's also the release of energy. So the most common, or maybe I should say the only possible nuclear fission reactions that we have had so far are with uranium 235 and polonium 239. Okay, so if you see the nuclear fission examples for these two, that those are the only nuclear fission examples that you should select as your answer. So in this case, you can see that uranium 235 is bombarded with a neutron, so it becomes unstable. It's already unstable, now it becomes more unstable, and then it splits into 2 smaller radioisotopes and releases a lot of energy as a result. So for a fission reaction to occur, the uranium 235 must be bombarded with a neutron with a very specific amount of energy. If that doesn't happen, fission doesn't start. And then nuclear fusion is when we combine smaller nuclei to produce a bigger nucleus. And then again, the very specific example that we know about is an example of fusion, and that does occur, is what happens in the sun, and that is going to be this equation right here. Okay, so if you are asked for an example of fusion, make sure that you only select this option. What we see here is that the lighter nuclei, the 2 hydrogen isotopes, are combining to make helium isotope. So just some of the things to remember about fission and fusion is that fusion produces way more energy compared to fission. However, fusion is also very hard to conduct because it requires very, very high temperature and extremely high pressure. So those conditions are very high to make and establish. And then with the fission, which is relatively easier to conduct compared to fusion, the problem is it also produces a lot of energy, even though less than fusion, but it is significant amount of energy. But the biggest problem with fission is that it produces a lot of nuclear waste, because it produces those radioisotopes that are then going to decay and keep decaying around us. So that's kind of the biggest problem of fission. Fusion is relatively safer compared to fission. Okay, so half-life. This is the amount of time that is required for any sample of a given radioisotope to decay to one half of what it started with. The thing to remember about half-life is that it always remains the same. So let's say you are starting with 10 grams, and after the first half-life, you are going to be left with 5 grams. And let's say it took you 2 years to go from 10 grams to 5 grams. Now, if I want to go from 5 grams to 2.5 grams, this is going to be my second, not my, but this is going to be the second half-life for that radioisotope, and this is still going to take 2 years. So whatever, it doesn't matter what mass you start with, the amount of time that it takes to go from that mass to one half of that sample is always going to be the same. So we are given the half-life of some radioisotopes in table N. And just remember that nothing can change the half-life. So you might be tricked with the question where they might ask you that, what if you change the temperature? What if you change the pressure? How is that going to impact the half-life? Just remember that nothing is going to have an impact on the half-life. Like, the substances keep on decaying like normal, no matter what the circumstances are. So half-life is always going to stay the same. When you are asked to solve any half-life problems, remember your basic trick. Your first step should always be to calculate the number of half-lives, because that is going to kind of lead you towards the next step. So here are some examples of the half-life problems. We have 100 grams of a radioactive isotope that decays to 12.5 grams after 90.7 days. So what was the number of half-lives? So if we are going from 10 grams to 50 grams, then to 25, then to 12.5, it took us 3 half-lives. Okay, and that's basically all that the question is asking. So we took 3 half-lives to go from 100 grams to 12.5. Next up, it's saying 100 grams of radioactive isotope decays to 12.5 after 90.7 days. What is the half-life? So once again, we go ahead and say that when we go from 100 to 12.5, that was 3 half-lives. So if it took us 90.7 days for 3 half-lives, how much would that be for 1 half-life? So we just do 90.7 divided by 3, and that gives us 30.2 years. This is 1 half-life. All right, next up, what is the total number of years that must pass before only 25 grams of an original 100-gram sample of carbon-14 remains unchanged? So once again, your first step should be to calculate the number of half-lives. So we are starting with 100 grams and going to 25 grams. That's going to be 2 half-lives. So if 2 half-lives have passed, and according to table N, we know that 1 half-life of carbon-14 is 5,715 years. We just take that number, multiply that by 2, and that gives us the time for 2 half-lives. You can also get some questions about the mass that we started with or that's left or stuff like that. So a radioisotope has a half-life of 10 days. 1 gram remains after 40 days. What was the initial amount that we started with? So once again, count the number of half-lives. So it's saying that if the half-life was 40, half-life is 10 days and 40 days have passed, that means that is 4 half-lives that have passed already. So if right now we have 1 gram, before the 4th half-life we had 2 grams, before that half-life we had 4 grams, then we had 8, then we had 16. So that means we most likely started with 16 grams. If we have an original sample of carbon-14 that was 50 grams, how many grams will be left after 17,145 years? So according to, you have to first, remember, determine the number of half-lives. According to table N, the half-life of carbon is 5,715 years. So we just take the total time that has passed, divide that by 5,715. That tells you that 3 half-lives have passed. So now, if the original sample was 50 grams, after 3 half-lives, it's going to be 6.25 grams. So you can just like do your arrows thing. All right, finally, we have iodine that has a half-life of 8.07 days. A 10-gram sample was allowed to decay for 32 days. So what fraction of this sample remained? So first of all, let's determine the number of half-lives that have passed. So we take 32, divide that by 8.07, we get 4 half-lives. So for the fraction, all you have to do is just do 1.4 to the power, 1 half to the power of 4. This basically means you have 1 by 2 times 1 by 2 times 1 by 2 times 1 by 2. So that's 2 times 2, which is 4. 4 times 2 is 16. It should, and 16 by 2 is 32. So it should be 1 over 32, not 1 over 16. All right. So another way to think about it is that, let's say you started with a sample of 1. After the first half-life, you were left with 1 half. After the second half-life, you were left with 1/4. After the third half-life, you were left with 1/8. And then after the fourth half-life, you were left with 1/16. Okay, moving on to the uses of radioisotopes, which is the last thing in this unit. So radioisotopes can do have a lot of medical uses. So make sure that you remember all of these uses with the specific radioisotopes, because you can get the questions where they'll be like, what is the use of this radioisotope or something. So this is something that you have to memorize. So technetium-99 is something that can be used to detect brain tumors. So maybe like what we said in class. So tech in technetium and detect in for the brain tumors. And then iodine 131. This is something that is used to diagnose and treat thyroid disorders. This is more of a general knowledge thing that we should all know. You should consume enough iodine so that you don't ever run into any thyroid problems. And then we can use radium or cobalt 60 to treat and also diagnose cancer. Then for food storage, cesium-137 is used to kill bacteria. So you can think about maybe cesium-137 sees the life of bacteria, stuff like that. So kind of to keep the food safe for longer periods of time. And then for radioactive dating, meaning finding the age of either living or non-living things, we can use uranium and lead-206 to find the age of geological formations, for example, rocks. And then we can use carbon-14 to find the age of once living substances. And that's because all living substances or organic compounds have like the carbon-based substances in them. So we all have abundant amounts of carbon in us. And then we can use phosphorus 31 as a tracer to kind of see the function of different fertilizers. Alrighty, so this was the end of your nuclear chemistry and also the end of the Regents review series. I hope we all got at least some use, some benefit from this. So I'll hopefully see you all very, very soon.